Okay, so thanks everyone for coming. Thanks for the introduction. This is joint work with my advisor in Potsdam, Alexandra Carpentier, who's not here, and Samorik Poutoufe, who is in Amsterdam, but I don't think he's in the room. So we are going to talk about active learning under non-parametric assumptions, and we're going to be interested in two questions. The interaction between two different noise parameters in this non-parametric setting, and the adaptivity to these parameters. Okay, so I assume you're all quite familiar with the usual passive learning setting for classification, where the learner receives a data set that contains features and labels of a certain size, and he has to output a classifier with good risk. In active learning, the setting is slightly different. Instead of getting the entire data set at the beginning, he can actively query labels for any features that he wants in the domain, which is going to be 0, 1 to the d in this talk. So most important results in active learning, and there are too many for me to list them all today, are concerned with the parametric setting, and it's now fairly well understood under what assumptions the gains of active learning are over passive learning, which is the obvious baseline that you need to compare to, especially whenever the noise in the labels is not too high. So today we're going to consider a non-parametric setting, which lets us encode a little more structure in the noise and characterize different regimes of noise. So what's the noise in my problem? It's represented by this eta of x, which is simply the conditional of the labels that I see when I query in X. So just so that we're all on the same page, if I choose to ask for a label in feature X, I get a Y, which is in 0, 1, drawn from a Bernoulli law of parameter eta of X. So the first non-parametric assumption I'm going to make is that this regression function eta of X is Hölder smooth, of smoothness alpha. So the assumption is a little technical, but for now you can just think of it as all the derivatives of eta up to order alpha are bounded. A second non-parametric assumption I'm going to make, which was introduced by Tsibakov, is called the Tsibakov noise condition. And it tells me that there exist two constants C and beta greater than 0, such that for any delta strictly greater than 0, this is true. And so this inequality bounds the measure under Px of the zones that are delta away at most from the threshold 1/2. So threshold 1/2 is important because if eta of x is greater than 1/2, the optimal classification rule that I can do in a point x is to predict class 1. Okay. And so this assumption tells me that for delta greater than 0, this measure grows as delta to the beta. So we're going to see a little example. But let me just say that alpha and beta allow us to characterize the continuum between easy and hard problems. So on the left of the screen, you can see an example where I have small smoothness, meaning that eta can vary greatly in a very short scale in terms of x. So this is a hard problem because there is a little less local structure to use and decide what is the classification rule that I should be outputting. On the right, you can see a different example with small beta, meaning that eta spends a lot of time around the decision boundary 1/2, and so it's also hard to output a good classifier in this setting. But you can see that here, my function is more smooth, so maybe I can gain from that. So what you need to remember is simply the following rule of thumb. The greater alpha, the easier it is. The greater beta, the easier the problem should be. So this raises two natural questions. How do these two parameters, alpha, beta, and d, the dimension of the space, interact in terms of hardness of the problem? And can we be adaptive to these parameters? Meaning, if I do not know these parameters at the beginning of the game, can I adapt to them and take advantage of easier situations while being robust to the harder cases? So this setting was first studied in the really nice work of Minskar in 2012 under a few more assumptions. So first, I'm going to say that Px is uniform. When I talk about Px, I talk about the measure under which I calculate the risk and the excess risk for my classifier. A second assumption, which is more restraining, is a self-similarity assumption on eta. What this means is that at any scale that I look at my function eta, it has roughly the same smoothness, meaning that if I detect the smoothness at a higher scale, I can use it to refine my exploration at a smaller scale. The assumption is technical, but it cannot be removed, and it's intrinsic to the techniques that are used in the upper bound in this paper. So a first theorem allows us to characterize a little the interaction between the parameters. So for smoothness smaller than 1, under this self-similarity assumption, there exists a strategy that achieves this excess risk. Minskar also shows the lower bound, so this rate is tight. And for us to understand the interaction between the parameters, let us look at the passive baseline. So basically, this setting was introduced and studied in a really nice paper by Odibert and Sibakov in 2007. And the rate is the same, except that I have D here instead of D minus alpha beta. So the advantage of passive learning can be seen as a sort of dimensionality reduction, in the sense that if I can detect the regions close to the decision boundary, I can focus on them and use more labels in this region and gain an advantage over the passive setting. For alpha greater than 1, there is a very interesting transition in the upper bound in the work of Minskar. And instead of having D minus alpha beta, I have D minus beta. So you can think of it as being D minus smoothness 1 times beta. We're going to talk a little more about these things later. But Minskar conjectures that this rate is tight and there is no lower bound. The only lower bound that exists for alpha greater than 1 is this lower bound here. That's always was for alpha greater than 1. So this raises three natural questions, which are the 3 points highlighted in red. What happens if we drop the uniform assumption on Px? What happens if we consider general eta, meaning the only assumption I make is the Holder smoothness on eta and not the self-similarity assumption? And is the rate tight for alpha greater than 1? So our contributions, statistical contributions, can be summarized in the following way. So under milder conditions, we establish new rate regimes. So for Px uniform, say same assumption as in Minskar, we achieve the same upper bounds, the same rates, without the self-similarity condition. So it means that under the exact same assumptions as considered in the passive setting, we show that active learning has outperforms a passive strategy. We verify the rate transition for alpha greater than 1 only in the case beta equal 1. And we show that there is indeed a rate transition. I'm going to talk about it at the end. And finally, we consider the case where Px is unrestricted, meaning not only is it not uniform, but it can be as bad as it wants, as long as it satisfies the Tsibakov noise condition, which is also an assumption on Px. And what we show is that the active learning minimax rate is faster than the passive rate. And again, there is this interaction with this alpha beta dimension term. Okay, so what's a natural strategy when you look at this problem, which is the strategy that was developed in the paper by Minskar? Suppose that after I have sampled many labels in my domain, I have access to a confidence band here on eta. So this means I do not know what eta is exactly, but I know with high probability that it's in this band. And suppose in my stylized example that my decision is only do I query in x1, x2, or x3. So the strategy is basically if the confidence band here does not intersect with the boundary 1/2, I know with certainty the true label of this point. and I do not need to query it anymore. So here, I will only query x2. So if you extend this strategy, this intuition into an algorithm, you get the strategy in mean score, and you will refine your exploration and only explore in places where the confidence bound intersects with the boundary. Okay, so this seems like a fairly good idea for an algorithm. The problem is that optimal confidence bands, and what I mean by optimal is that a confidence band that scales with the smoothness which is unknown to the learner, do not exist in general over Hölder spaces, and there are many nice and classical results in statistics literature for impossibility results, and you need extra assumptions. So for example, this sort of self-similarity assumption that's considered in mean score for such confidence bands to exist and for us to use them. So what we introduced in this paper, our algorithmic contribution, is a new generic adaptation strategy for nested smoothness classes. And what we do is that we carefully aggregate the labels of estimates of a non-adaptive subroutine over increasing values of alpha 0. So that's what we're going to focus on right now, and this is going to become clear really soon. So I'm going to present our algorithms, and first I'm going to start with the non-adaptive subroutine. So by non-adaptive, I mean the following. I mean that we know, the learner knows, that eta is alpha smooth. So the learner can use alpha in the algorithm, and eta is indeed alpha smooth. Okay, so let's consider a cell C of side R with center XC. Natural strategy for alpha smaller than 1, where I can use a simple mean estimator, is to do the following. So I'm going to query for T labels in XC, the center, and I'm going to estimate eta of XC with simply the mean estimator. And with high probability, I know that my estimator is going to be close to the true value of eta in XC, and it's going to scale as square root 1 over T, as we all know. Okay, so now how do I use the smoothness to go from a local property of eta in XC to a global property that's in the entire cell? So for alpha smaller than 1, you can think of the smoothness as the following condition. Eta changes on C by at most R to the alpha. So this means that for any X in my cell, if I have access to an estimate in XC, I can say something about the true value of eta in X, and it's related to these two terms, this stochastic term, which depends on the number of labels I've queried in XC, and this smoothness term. So what I'm going to do is we're going to sample in XC a number T times such that T is of order R to the minus 2 alpha, such that these two terms are of the same order. So the stochastic term and the bias are of the same order. And then we can safely label this cell as the same label as the empirical label in XC if this is true. Why can we do that? Because if the estimate of eta in XC is far away enough from 1/2, then I know that I have a big enough margin to say that for any X in this cell, the true label in X is the same as the empirical label in XC. Okay, so I only label a cell if I think that there cannot be a single point that has a different label. Otherwise, if this is not true, it means that we're looking at a too big scale and we need to refine C and repeat this intuition over smaller regions. Okay. So we can implement the previous intuition of a hierarchical partition of 0, 1 to the D, and we go deeper in this hierarchical partition, and that's why we use the Tsibakov noise condition and the assumption on Px to bound the number of active cells as we go down in this tree. So if I have a budget n, my final output by this algorithm has the two following properties. So first, it outputs me correctly labeled regions of the space. So here in red, class 1, in blue, class 0. And I know with high probability that this is the true label for all the points here. Second, my strategy is allowed to abstain in certain regions of the space, so here in white. So this means that I can avoid making a prediction when I'm not sure enough. Okay. And what I claim is that this region has the optimal size, meaning that if I were to recommend any class in this abstention region, I would still reach the minimax rate that I showed earlier. So in a sense, I have already labeled everything I can label under this budget, and I cannot do better in the abstention region. So let me say just a quick word on the alpha greater than 1 case. The intuition is similar, but we need a higher order interpolation on the cell, meaning I'm not going to be able to exploit any smoothness if I just sample all my points in the center of the cell. Okay, so how do we go from this non-adaptive procedure to an adaptive one? The key idea is the following. If eta is alpha smooth, then eta is also alpha prime smooth for any alpha prime smaller than alpha. So it's the classical nestedness property of Hölder classes. And so what I just showed is that if I call my subroutine with a too small parameter alpha prime, it still returns correct labels. Now the thing is that I'm not going to have an abstention region of the optimal size, but I don't mind so much because I still know what I don't know, and the labels that have been returned are all correct. So the procedure is fairly simple. We aggregate the labels for increasing values of alpha prime that we use to call the subroutine. So imagine that alpha 1 is smaller than alpha 2, and I get these labeled regions from the run with alpha 1, and this labeled region for the run with alpha 2. So the first rule is that I preserve the labeled regions by the run with the smaller smoothness, meaning here, the labeled regions are in disagreement with the run with the smaller smoothness, so I keep the red class here. Here, they are not in disagreement, they are in the abstention region. So as I said before, I could, if this abstention region is of optimal size, I don't really mind what I predict here, but I still aggregate in this fashion. And so when I combine these two labeled regions, I get this aggregated classifier. So the correctness property that we have is that imagine that in this grid of alpha parameters, I have the true alpha I somewhere. Then the labeling has optimal error. Why? Because whenever I run the procedure with a too small parameter, I never add mistakes. Then I reach the true parameter and I have the optimal size for the abstention region. And then I do not have any guarantee on what happens if I run the procedure with a too big smoothness, meaning eta is not in the smoothness class. But as I said, I don't mind. It doesn't cost me so much. So the error remains small. The implementation is fairly simple. We just have a grid of parameters that asymptotically covers all the parameters, and we divide our budget to launch many runs of the subroutine, and we use this aggregation procedure. Okay, so what we just proved is that without self-similarity assumptions, there exists an active strategy that reaches these rates. And these rates are all tight. Okay, so the new lower bounds that we prove are the following. So the first lower bound is directly inspired from techniques in Sibakov and paper by Castro and Novak and Minskar. It's fairly simple to obtain. So let me say a few words on this lower bound. What we show is that there is indeed a rate transition. So we consider the case beta equal 1 and alpha greater than 1. Shortly, what we can do is that along one direction, eta is allowed to cross the threshold 1/2 linearly while still being alpha smooth, meaning that if I'm linear in a direction, in this direction I'm infinitely smooth, and so I just need to to create my lower bound such that eta oscillates in these order-free directions, so d minus 1 directions, and so d minus 1 acts as the effective degrees of freedom, and this is how we prove the lower bound. Okay, so as a conclusion, we recovered the active rates in in active learning under less restrictive assumptions. We confirmed a conjecture transition for alpha greater than 1. We established new minimax rates for unrestricted PX. And perhaps most importantly, we introduced a new generic adaptation framework for nested classes. So an interesting extension is that our framework also yields the first adaptive procedure under slightly different non-parametric assumptions in active learning, which characterize the smoothness of the boundary, which was first considered in a COLT paper 10 years ago by Castro and Novak, and there was no adaptive procedure before. So I'm done. Sorry, thanks.
So maybe time for a quick question while the next speaker is setting up.
Sure. No, we are.
Can you repeat the question, please?
We are completely adaptive to beta. And we're also completely adaptive to the different cases in terms of PX, meaning we do not need to have an infinite amount of unlabeled data to estimate PX, for example, for the algorithm to run.